Okay, this will be a brief description of slew bearing design in a program I wrote in AutoCAD to design slew bearings, which is kind of bearing which can take a lot of axial force and a lot of bending moment instead of just a radial force. And it's because they have these rollers in a V-shaped in two V-shaped troughs. Like, for example, you can see that if I am to erase these two things here, these dudes, you can see that V-shaped trough, and that allows the bearing to support a lot of bending moment and a lot of axial force. And they're used in things like excavators and wind turbines. And I became interested in them after I saw a video about a guy who was designing them for 3D printers. And he was doing it with cylindrical rollers, and it was only at the end he said, well, they should be conics, they should be cones. And so I said, well, damn, I'm going to design it with cones, because it was obvious that you shouldn't use cylinders. So I went and I went about to write a program. Well, first I designed my own slew bearing manually. I was able to do it, and then I wrote a program to do it. So the first thing I did is that I did it. Whoa, hello, where'd everybody go? Oh, hold on, I want to have them. First thing I did is I made a model of it, of the bearing, of how it actually works, and they're cones because all the cones got to meet right at the center of the bearing. Well, at the bottom, along the radial axis of the bearing. And in order to get a slew bearing that will resist force in both directions, you got to have cones which point in both directions, as in here, as seen in here. So, some of them will roll when there's a bending moment in one direction, or a radial force in one direction, and then the other ones will work when there's a bending moment or a radial force in the other direction. So I realized that I was making things a little too complicated. I could actually describe everything with this here. And what I learned from this are the relations between these three angles. Alpha is determined solely by the number of bearings you have, rollers that you have in the bearing. And then there's these other two angles, which are beta, and another one I called eta. And those are actually determined by the fact that the angles have to be correct for both sets of these bearings. One pointing one way and the other set pointing the other, alternating. They have to line up correctly, and so this describes the geometry to have them lined up correctly. And you get to a formula which basically says from over here that beta plus 90 has to equal 180 minus beta plus eta in order for these angles to be equal, which they have to be for both sets of conic bearings to work in the same space. And that's simplified to 2 beta minus 90 minus eta equals 0. But eta is dependent upon beta and alpha. Alpha stays constant. There's alpha again. Alpha stays constant because that's determined by the number of bearings. But eta is dependent upon beta, because what happens is when this angle, when the angle beta changes, the angle of eta changes as well. So I solved for eta. Eta can be solved explicitly for alpha and beta. So I take that explicit equation for eta, and I substituted into this equation, and I got a non-dimensional equation which I then used to put into the Newton-Raphson method for root finding, which is the simplest one that you can use, and it works very well if you know approximately where the root is, which we do. And don't worry about that, that's something else. In any case, so once I had the equation to figure out the angles, once I have alpha, which is determined by the number of bearings, I can then use these equations here with the Newton-Raphson method in order to find the solution to beta and eta as well. And once I know the solution to beta and eta as well, well, then I can figure out these vector points right here, which will allow me to draw the forms I need in order to revolve into these shapes of the bearings and the races. And so I wrote it in AutoLisp, and this is the program right here. I have it on GitHub, and I'll leave the link in the description in case anyone wants to use it. There's a few things you got to do. You got to enter the tolerances of your 3D printer in order to account for that. Where is that? You enter it. You enter those tolerances right. They're around here somewhere. Oh, there they are. I'll figure out where it is. In any case, so here I'll show you the program now. So basically, go towards the origin of a blank drawing, and then you type, bearing dialog. And then right now, like for example, this bearing has number 30 rollers. I'll put that up to, let's go up to 60. Let's double it. Let's go crazy and see what happens. We'll draw it. And sure enough, look at that. Now we got the bearings, got 60 ball bearings, but now look, his width is too great. So let's change the width. Okay, where's the width? Where the hell did it go? There it is, thickness. Okay, I'll say that could go down to 12 maybe. Alright, that looks a little bit better. And now maybe we want to make it a little bit smaller. So let's bring all the radii down. So let's see, we'll say the bearing design radius. Let's take that down by 15, so that'll be 35. And then we got to have the inner radius go down by 15, so that'll be 16. And the outer radius by 15, and that will be 48. And then we'll draw it. And sure enough, yeah, that did it. And as you can see, the parts should all be ready to print. Yeah, you can print all the. See, they're almost round. That's because I scaled it down, but I didn't change the fillet radius. So I'll go back, and I'll just change the fillet. Where's the fillet radius? There it is. Let's take that down to 0.5. Draw. Yeah, that looks a lot nicer. And so that's how you can use my program to design your own bearings. I'll leave the the link to the GitHub repository in the description. And yeah, that's about it. I hope you enjoyed the video, and feel free to help yourself to the code. I printed out a whole bunch of bearings. They work very nicely. Alright, have a great day or night, as the case may be.